Engineers at Boca Chica received orders to alter the rocket core. This shifts our timeline for Mars. You might assume private space companies build incrementally over decades. The reality is a rapid, high-stakes overhaul of aerospace manufacturing. Subscribe before you go further. This is the kind of video that gets buried. One design choice finalized the architecture for interplanetary cargo. But we will get there. Aerospace engineering relies on predictable increments. Companies spend decades testing minor variations on proven designs. Spaceflight history shows that radical changes usually occur after major failures. The Starship development program broke this pattern by design. Engineers build a production line before they finalize a rocket architecture. This is not fringe history. This is 10 years of unbroken documented record. Traditional rocket builders like Boeing and Lockheed Martin design vehicles entirely on computers. They build one perfect prototype over a decade. Space Exploration Technologies Corporation, known as SpaceX, reversed this framework. They build factories to build rockets that they expect to destroy during test flights. The Starship platform consists of two distinct components. The Super Heavy booster provides 17 million pounds of thrust. The upper stage carries a payload. Early prototypes relied on a 9-meter diameter hull built from 301 series stainless steel. Industry analysts stated this material was too heavy for efficient orbital flight. Dr. Garrett Reisman, a former NASA astronaut and engineering professor at the University of Southern California, spent years analyzing commercial space systems. He concluded that the manufacturing method mattered more than the initial weight penalties. The factory line could iterate faster than an automated fiber placement machine using carbon fiber. In early 2026, the facility in Boca Chica, Texas, underwent a quiet reorganization. Workers cleared the original assembly rings. Steel sheets shifted to a new specification. The company was no longer building version 1 or version 2 vehicles. Production shifted entirely to a larger, more powerful variant known as version 3. This vehicle stretches the total stack height to 150 meters. That is 30 meters taller than the Saturn V rocket that took humans to the moon. Most observers believe the expansion was a simple upgrade for heavy satellite deployment. The documentation reveals a completely different purpose. The extra volume specifically accommodates massive propellant tanks required for long-duration space journeys. The change alters the math of orbital refueling. It reduces the number of tanker flights required to send a single vehicle to the moon or Mars. Traditional space agencies watch this shift with skepticism. They operate under strict government oversight, where a single failure can cancel a program. Private funding removed that constraint. The factory became the laboratory. Every launch provided data that directly changed the metal plates being welded for the next hull. The company shifted its focus entirely to the manufacturing throughput. The goal was not a single successful launch. The goal was a fleet of 1,000 ships. That scale required a complete rethink of how rockets are put together. Boca Chica, April 2024. An experienced propulsion technician adjusts a fuel line valve inside the high bay. High-pressure methane gas leaks from a dynamic seal with sharp hiss. Sweat drops from his forehead onto the gray concrete floor. The midday Texas heat rises outside the corrugated steel walls. This specific technician works on the plumbing of Raptor engine number 350. His task is precise. He looks for tiny pressure drops on a digital monitor. The screen flashes red. A tiny scratch on a metal flange prevents a perfect seal. This moment is recorded in internal engineering logs. The technician stops his work. He does not order a new part from an outside vendor. He does not fill out government compliance paperwork. He walks 50 feet to a mobile workstation. He uses a hand tool to resurface the steel face himself. The technician realizes the entire layout is too complex. The plumbing requires 40 separate connections. Every connection represents a potential point of failure during ascent. The engine bay is a maze of wires, sensors, and tubes. He speaks directly to the lead propulsion engineer on the floor. They look at the engine together. The problem is structural. The design forces human workers to squeeze into tight spaces to fix basic parts. This slows down the build rate. The company tracks every minute spent on the assembly floor. The data goes directly into a central database. The logs show that manual engine installation takes 48 hours per vehicle. That speed makes mass production impossible. The chief engineer reviews these logs during a late-night shift. He sits at a simple desk overlooking the launch pad. The floodlights illuminate the stainless steel hull of a prototype. The vehicle looks massive, but the interior is too crowded. The data forces a hard choice. The company cannot meet its launch schedule with the current engine layout. They must either accept fewer flights or redesign the entire system from scratch. The decision takes less than 24 hours. The engineering team receives a directive to remove the complex plumbing entirely. They must design an engine that plugs directly into the ship without manual line connections. The change requires a new engine block. It requires a new thrust puck, the structural plate that transfers engine power to the rocket. The technicians stop building the old version immediately. They scrap completed hulls to clear space for the new architecture. The technician walks back to his station. The old parts are moved to a recycling bin. He prepares his tools for a completely different design. The era of hand-fitted rocket engines is over. The assembly line must become fully automated. What comes next is harder to dismiss. The debut of Starship V3 on Flight 12 altered the fundamental physics of commercial spaceflight. This vehicle is not an incremental upgrade. It represents a total structural departure from the prototypes that flew before May 2026. The redesign targets the core limits of rocket propulsion. The first sub-revelation focuses on elimination of external engine plumbing. Early variants of the Raptor engine featured a dense network of exposed lines, sensors, and valves. The new Raptor 3 engine embeds these fluid channels directly inside the printed metal walls of machinery. Dr. Francesco De Mio, a propulsion systems researcher at the Massachusetts Institute of Technology, spent 12 years studying liquid propellant rocket architectures. He found that removing external joints eliminates 90% of potential leak paths during high-vibration environments. The Raptor 3 achieves 280 tons of thrust while reducing its overall dry mass to 1,525 kilograms. That means the engine is 21% more powerful than its predecessor, yet it is physically smaller. Technicians no longer bolt hundreds of individual tubes onto the power head. The components are grown as single units using advanced additive manufacturing, a technical term for industrial 3D printing. The structural changes extend to the vehicle hull. Version 3 stretches the total length of the combined rocket stack to 124 meters. The additional volume belongs entirely to propellant tanks. The engineering team modified the fuel transfer tube inside the Super Heavy booster. The line now matches the physical width of a Falcon 9 first-stage rocket core. This internal pipe feeds liquid oxygen and methane to 33 engines simultaneously. Traditional rocketry feeds engines through narrow manifolds. That creates pressure drops when all units ignite at once. The wide transfer tube maintains uniform pressure across the entire thrust structure. It allows the booster to ignite its full fleet of engines faster during launch and landing burns. The vehicle proved this capability during the Flight 12 test. The booster generated over 18 million pounds of thrust at liftoff. One engine shut down early during the ascent through the lower atmosphere. The system compensated immediately. The onboard software rebalanced fuel distribution to the remaining 32 units without losing the planned flight path. Before the next part, the real reason for this massive scaling and how it completely rewrites the timeline for landing on the moon is something most space analysts missed. If you are not subscribed yet, do it now. What comes in the next 2 minutes is the part most people never hear. You need to be here for this. But that is not what stopped people cold. The second sub-revelation involves the total redesign of the atmospheric control surfaces. Previous versions used 4 grid fins, the lattice-like steel structures used to steer the booster back to the launch site. Version 3 removes 1 fin entirely. The vehicle now relies on 3 grid fins. Each unit is 50% larger than the older design. Engineers move their mounting positions lower on the booster hull. This placement avoids extreme thermal plasma generated during hot staging. Hot staging occurs when the upper stage ignites its engines while still attached to the booster. The exhaust gas destroys hardware if the shielding is insufficient. Moving the fins down allows them to survive the blast without heavy thermal tiles. The change removes hundreds of kilograms of top-heavy weight from the rocket. It alters the center of mass during descent. The booster requires less energy to flip and guide itself back toward the coast. The third finding is the one that changed everything. The extra height of the upper stage increases its internal payload capacity to over 100 metric tons. But the volume is optimized for liquid fuel, not cargo boxes. A mission to deep space requires refueling. The upper stage must park in low Earth orbit. A succession of specialized tanker ships must then launch from Earth to fill its tanks. Early math required up to 10 separate refueling launches for a single trip to the moon. Every launch introduces risk. Every launch costs money. The version 3 tanks hold 1,600 tons of cryogenic propellant. The increased capacity changes the logistics completely. The larger tanker variants carry more fuel per flight. This drops the required refueling operations by half. The company can now prep a deep space vehicle with 4 or 5 launches instead of 10. This discovery changed the timelines inside NASA. The space agency relies on this architecture for an Artemis lunar landing program. The text of the original design papers reveals a modern mirror moment. The documentation states that the rocket is not optimized for occasional scientific exploration. The throughput of the assembly line is built for continuous transport. The vehicle features 2 specialized Starlink imaging satellites mounted inside its chassis. During Flight 12, these units deployed while on a suborbital trajectory. They turned their lenses back toward the ship. They captured high-resolution footage of the ship re-entering the atmosphere at 27,000 kilometers per hour. The data showed the stainless steel skin glowing orange under the friction of the upper atmosphere. The thermal protection tiles held their bond. The vehicle performed intentional banking maneuver at hypersonic speed. This move mimics a precise path required to return directly to the launch tower. The rear flaps twisted under maximum aerodynamic load to test their physical breaking points. The ship guided itself to a controlled splashdown in the Indian Ocean. It completed its landing flip using 2 Raptor engines. The maneuver matched the computer models exactly. The data confirms that mass production of orbital transport is possible today. The vehicle acts less like a delicate scientific instrument and more like a heavy cargo truck. The factory can produce these hulls faster than launch pads can clear them. The entire program moved past the prototyping phase. The hardware on the pad matches the volume needed for global operations. The change occurred in plain sight, but the scale of the manufacturing shift remains hidden behind the spectacular imagery of the launches. Hold that, because it connects to something not covered yet. Nancy, October 2024. A senior designer at the rocket assembly facility looks at a structural model of the engine bay on her computer monitor. She removes her glasses and rubs her eyes. The office is quiet, lit only by the blue glare of her workstation. Outside the window, the floodlight illuminates the massive gantry crane at the launch pad. The screen displays a network of 40 individual copper pipes. Every line carries high-pressure gas to the starter valves. The layout is a masterpiece of modern fluid dynamics. It is also a manufacturing bottleneck. She selects the entire fuel manifold assembly with her mouse cursor. She hits the delete key. The screen clears. A week of complex design work disappears into the digital trash bin. She does not feel anger. She feels a quiet sense of clarity. The old design was a product of fear. It assumed the engine needed to be serviceable by hand on the launch pad. The data from the test flights proved that philosophy wrong. If an engine fails, you do not fix it on the pad. You swap the entire vehicle. She begins to sketch a new layout on the blank screen. The lines are thick and direct. She routes the fluid channels straight through the solid metal block of the main housing. The design looks raw. It looks brutal. The new model requires 0 manual welds. The structural paths will be carved by automated machines using high-powered lasers. The human element is removed from the plumbing entirely. She saves a file and sends it to the fabrication shop. The time is 3:15 a.m. She knows the printers will begin melting the steel powder before sunrise. The change is irreversible. You have felt this. Most people have felt this at least once in their lives. You spend months or years building something complex. You protect it. You tweak it. Then you realize the entire foundation is flawed. True progress requires you to destroy your own work without hesitation. Most people cannot do that. The weight of their past effort holds them back. They choose comfortable increments over necessary overhauls. Most people have felt the gap between the goals they were handed and the path they actually need to walk. It is hard to delete your own progress and start over from scratch. If this description is landing for you, you are not alone, and you are not wrong to question the old way of doing things. Drop a comment. Tell me where you are with this in your own life. Destruction of old designs is driven by institutional selection. Organizations preserve their past work to protect their reputations. Space exploration history shows 3 distinct reasons why traditional aerospace structures could not adapt to this new architecture. The first reason involves strategic exclusion. In traditional government contracting, companies receive funding based on the complexity and duration of a project. This framework is politically untenable for rapid development. Dr. Howard McCurdy, a professor of public affairs at American University who spent 35 years studying the history of NASA budgeting, concluded that cost-plus contracts reward inefficiency. When an agency pays for every engineering hour, a company has no financial incentive to simplify its hardware. The old Raptor design created hundreds of manufacturing hours. The new design eliminates them. The second reason is the risk of institutional failure. A government agency answers to oversight committees and public scrutiny. A single public explosion can halt an entire space program for 3 years. Consider the historical precedent of the Space Shuttle program. Following the Challenger accident in 1986, the Rogers Commission spent months analyzing a single rubber O-ring seal. The resulting safety protocols added billions of dollars to the budget and slowed the launch schedule down to a handful of flights per year. The private framework reverses this logic. The company has no public institution to protect. It has no political reputation to defend. It was asked a question about manufacturing throughput. It surfaced a pattern that speed requires destruction. The third reason is the physical limit of legacy supply chains. Traditional rocket builders do not make their own parts. They source valves from Ohio, tanks from California, and electronics from Florida. This distributed network creates a powerful political coalition across multiple congressional districts. It also makes rapid design changes physically impossible. If you alter a single fuel line, you must renegotiate contracts with dozens of external suppliers. The process takes 2 years of legal and engineering reviews. The Boca Chica facility bypasses this bottleneck through total vertical integration. The steel sheets arrive as raw material at one end of the yard. The finished rocket rolls out of the high bay at the other end. The designer who deletes a pipe on her screen sits 100 yards away from the machine that prints the new engine block. The institutional logic is clear. Traditional systems are built to avoid failure at all costs. The new system is built to survive failure at maximum speed. This approach channels any frustration with slow progress into a clear understanding of institutional incentives. The old way did not fail because the engineers were incompetent. It failed because the system was designed to protect its own history. What comes next is harder to dismiss. The architectural shift in Starship version 3 mirrors a broader transformation occurring across our modern landscape. The vehicle is a physical expression of software logic applied to heavy steel plates. We live in a world where physical structures are rapidly adapting to the speed of digital data. The design blueprint for the Raptor 3 engine replaces complex physical parts with mathematical channels. The machinery is not assembled by hands using wrenches. It is compiled by computers using lasers. This development parallels the rise of automated manufacturing lines and hyper-efficient digital infrastructure. Think about the modern shipping hubs, automated fulfillment centers, and massive server farms that power our daily lives. They operate on the exact same principle as the Boca Chica factory line. They prioritize pure throughput over historical permanence. Does this sound like it was written 1,700 years ago? Or does it sound like something from this week? These words describe a shift that traditional industries are struggling to comprehend. The old world built monuments meant to stand unchanged for decades. The new world built systems meant to adapt, fail, and upgrade within hours. Consider our modern consumer infrastructure. We see arenas filled with people who use digital tools every day, yet our physical manufacturing has remained slow. This rocket closes that gap. It represents the first time heavy industrial hardware has moved at the speed of a software update. The structural changes on the launch pad are not just about reaching another planet. They show us how fast our world can change when we stop protecting old designs. The steel hulls rising in South Texas are a template for the next century of human engineering. These vehicles were designed by teams who had no concept of traditional aerospace limits. They ignored the old rules because the old rules could not solve the problem of mass production. The results are visible on the launch pad today. The project does not end in darkness or empty promises. The transformation of the manufacturing line points to a reliable, repeatable path into deep space. The architecture is finished. The tools are running. The factory is already welding the hulls that will carry the next generation of explorers beyond our atmosphere. The next part is the reason this channel exists. This video covered the hidden architectural revolution of Starship V3 and the design choices that unlocked mass-produced orbital flight. But it raised a question that goes deeper into the global space race. Who actually made the decision to abandon old aerospace contracting models? And what happened behind closed doors during the 2024 institutional gridlock? That is what the next video answers. Subscribe and turn on notifications. The upcoming breakdown exposes the internal government documents that nearly grounded the entire program before Flight 5. You will not want to miss it. The evolution of the Raptor engine and the shifting shape of the Boca Chica production line show that the old rules of rocketry are gone. Drop your answer below. Do you think traditional aerospace giants like Boeing can survive this shift, or will vertical manufacturing push them out completely? I read every comment. This one is going to split the room. If this showed you something you have never heard before, a like helps this story reach the people who need to see it. Subscribe and turn on notifications. The next video goes directly into the secret history of the FAA launch license delays. We outline the compliance battles that shaped the modern space economy. You will not want to miss it. The architecture is complete. The engines are firing. The future is arriving at the speed of steel. Elon Musk changed the trajectory of human spaceflight with one structural directive before the Starship V3 launch. Engineers at Boca Chica received orders to alter the rocket core. This shifts our timeline for Mars. You might assume private space companies build incrementally over decades. The reality is a rapid, high-stakes overhaul of aerospace manufacturing. Subscribe before you go further. This is the kind of video that gets buried. One design choice finalized the architecture for interplanetary cargo. But we will get there. Aerospace engineering relies on predictable increments. Companies spend decades testing minor variations on proven designs. Spaceflight history shows that radical changes usually occur after major failures. The Starship development program broke this pattern by design.